Greetings everyone, and welcome back to my channel. This is the fourth video of a series where we will explore a variety of concepts and ideas regarding differential calculus, as well as their practical uses in real-life contexts. Today's topic is optimization using differential calculus. Optimization in this situation is the process of solving practical problems using the skills we have developed in the previous videos. It is often defined as making the best or most effective use of a specific resource. We will not be learning anything new in this video. No new concept, no new rule, or anything else like that. Today we will be finally applying the math I have taught you in the previous videos to solve problems you could actually encounter in real-life situations. As such, we shall skip the explanation part of the video and immediately begin with an exercise. Before we begin, however, I must stress that these exercises are more difficult by a considerable margin than the ones we have encountered in my prior videos. Let us begin with a classic optimization problem using differential calculus. Suppose we have an A4 paper, which is 21 centimeters wide and approximately 30 centimeters long. We will cut away 4 squares which are equal in size from each of the corners of that sheet of paper. Afterwards, we will fold the resulting flaps to create an open box. What should the side length of those squares be in order to maximize the volume of the resulting open box? It is quite difficult to understand this question in words, therefore I will illustrate it using diagrams. So, here we have our paper with the correct dimensions, 21 and 30 centimeters. And we proceed to remove the 4 corners. Those red lines are where we are going to cut the paper. Anyways, now we imagine those 4 corners to have disappeared, and we now fold the sheet to form an open box. Those blue lines are where we are going to fold. It will be an open box because, as you may notice, the cuboid will only have 5 surfaces. This is generally the first step in solving these kinds of optimization problems. It is recommended to draw diagrams to help your mind visualize the problem. The second step is to identify the independent and dependent variables, that is, the thing we are changing and the thing we are trying to calculate to find the answer to our problem. For that, we must reread the question. In order to maximize the volume of the resulting open box, how long should the lengths of the squares you remove from each corner be? Well, we are clearly looking to maximize the volume. Therefore, that will be the dependent variable, which we will label with a capital V. As for the independent variable, that is simply the side length of the squares we will be cutting out, which we will say is x. We will be changing the side lengths of the squares to maximize the volume. Now we may add x to our diagrams. Our next step is to write some algebraic equations to express the relationship between the independent and dependent variables mathematically, as well as to model our problem with a formula, which we will need to solve the problem. To begin, we know that to find the volume of a cuboid object, we need the product of its length, width, and height. Therefore, V equals the length times the width times the height, or V equals LWH. Good, but we have too many variables now. We must create a formula with only 2 variables, the dependent and independent one. The dependent one, the volume, is already there, but the side length, our independent variable, is not present. Hence why we must now write the length, width, and height of our cuboid box in terms of the side length x. Essentially, L, W, and H in terms of x. To do that, it is helpful to glance at the diagram once more. So, first we will look at the length. The paper is 30 centimeters long, and then we cut 2 squares with a side length of x from it. That blue line is the length, and we can label that with an L. And we have just said that the line L is 30 centimeters with 2 x's removed from it. Therefore, L equals 30 minus 2x. We now do something similar with the width. It is the shorter blue line in the diagram, and its size can be expressed very similarly to the length. namely it is 21 with 2x removed from it. W equals 21 minus 2x. Now, what about a height? Well, it isn't one of the blue lines. However, if we imagine folding the paper without the corners into a box, we realize the height is actually equal to the side length of the square we cut away. As a result, h simply equals x. If we now input our new smaller formulas for the dimensions of the box into the original formula for the volume, we obtain an expression and formula to find the volume in terms of x, which is precisely what we are searching. V equals 30 minus 2x multiplied by 21 minus 2x multiplied by x. A final thing we must do before continuing is to establish a domain for our independent variable. For those unaware, a domain is the set of all possible values for the independent variable of a function. Essentially, it is all possible values that can be inputted into it. Normally, if we had our function for the volume in terms of x, the domain would be any real value of x. You could input any number into this function. However, we have additional information about this function which must be considered. First of all, we know that we are cutting squares from each corner of an A4 paper. Knowing that, we can immediately say that the side length cannot be a negative number, because in real life you cannot have a negative side length. It is physically impossible. So, x cannot be any value a smaller than 0. But now the question is, can it be 0? Again, we must consider a problem where we cut squares from the corners. There, it says that we must cut something away from the corners. If the side length was 0, we wouldn't be removing or cutting anything. Effectively, regardless of the length of the sides of the square we are removing, we must cut something away. Therefore, x cannot be 0 either. In other words, x is greater than 0, considering both criteria. Additionally, there is an upper limit to the value of x as well. For instance, x cannot be 100 centimeters, as that is longer than the actual length and width of the paper. The smallest dimension of the paper is 21 centimeters, the width, and from that we will be cutting 2x. We cannot cut too much, as we must leave something there to have a flap and create the open box. From that, we may draw the conclusion that 21 minus 2x cannot equal 0 or anything smaller. It must be something greater than 0. We solve for x now, and at last we get that x must be smaller than 10.5. Having established that x cannot be smaller than 0, yet also not bigger than 10.5, we have our domain. X must be between the two values. X must be greater than 0 and smaller than 10.5. Now we have finally come to the part where we use differential calculus. We must find the maximum or minimum point of our function, which shows the relationship between the independent and dependent variables. Recall we have this function and its domain. Here is part of the graph of our function for v, the y-axis of this graph being the volume and the x-axis being the side length. The red area is the area within our domain, between 0 and 10.5, as you may see. Effectively, that is the only part of the graph we care about. Looking at the graph, we can immediately find the answer to our question for maximizing the volume. That top point is the highest volume for v in our interval. Therefore, it is the maximum value for our model. And from there, we can also find the x value, which offers this volume. So if you have a graphing calculator available, this is the quickest and safest method to finding the answer to our original question. However, we will assume you don't have such technology. To find a maximum volume without graphs, we will first have to find the derivative of this function. Although before that we must remove the brackets from our function, since we cannot find the derivative in this form. We do that and find that the derivative of our function is 12x squared minus 204x plus 630. Using this derivative, we must now find the maximum point. One thing you must learn from this is that at these maximum and minimum points on a function, the line always turns. It goes from rising to falling at maximum points, or from falling to rising at minimum points. These are some examples. A notable thing about them is that if we draw a tangent at the maximum and minimum points, it would be horizontal, meaning the rate of change and the derivative equals 0. That is always true. Thus, v prime, the derivative of our function for v, must equal 0 at the maximum point. We input that value of 0 into the front of our function, and now we must solve for x. For that, I recommend using the quadratic formula. In the end, we get that x equals 4.056 and 12.944. Immediately, we notice that 12.944 is outside the parameters of our domain. Therefore, we must ignore it, which leaves us only with x equals 4.056. Normally, we would now check whether point x equals 4.056 is actually a maximum point, because if we didn't look at any graph of the function, we wouldn't know if it was actually a maximum point rather than a minimum one. Recall when we make our derivative equal 0, we find both the maximum and minimum points on the graph. What we would now do is find the derivative when x equals 0 by substituting 0 for x into the derivative. We chose 0 specifically because doing calculations with it is extremely easy. We find that v prime equals 630, which is a positive gradient. 0, the number we inputted to get that gradient, comes before 4.056. Therefore, the gradient is first positive and then it is neutral. In almost all cases, this means that after the gradient will be negative. When we have a positive gradient, then a neutral gradient, and then a negative gradient, we have a maximum point. First the function rises, then it stagnates, and afterwards it falls. The other way around is a minimum point. In conclusion, our point x equals 4.056 is in fact a maximum point. Finally, we must complete the last step of this problem, interpreting the result and answering the original question. For that, we know that x is the side length of the squares we cut away from the paper, and 4.56 yields the highest volume. Thus, cutting squares with side lengths of 4.056 centimeters from each corner of the paper and then creating an open box out of it will offer us the maximum possible volume for this problem. This was the original question, if you remember, and it was looking for the side length of the square that would offer the maximum volume. Well, we know it to be 4.056 centimeters. Thus, the final answer to this question is just 4.056 centimeters. What I wanted you to learn from this exercise was the procedure for solving optimization problems where we are looking to maximize or minimize a quantity. Recall that optimization is for solving real-life problems, and therefore it is extremely important you understand how it works, since it is the type of question you're likely to see in an exam. First, you begin by drawing diagrams to help you understand the problem better. It is not crucial you do that, though I highly recommend it. Next, you must identify the independent and dependent variables. You continue by using the two variables to write down algebraic formulas modeling the problem. You must also find a domain for your function, and to proceed, you use your knowledge of differential calculus to find the maximum or minimum points on the model function you're looking for. And finally, once you're done with everything, you end by interpreting your results and answering the original question to the problem. Follow these steps and you will be able to solve all optimization problems for differential calculus. Well, this was this edition's video. I do apologize for the late upload and the shorter video, but I have been a little ill and didn't have much time to work on it. Irrespective of that, I certainly hope my video has helped you understand what optimization is and what the procedure is you must employ to solve those types of problems. Thank you very much for watching. If you enjoyed, leave a like and comment, and give me some feedback on the quality of my video and my teaching. Furthermore, if you have any questions, you may ask them in the comment section. Have a wonderful day and farewell.